With a brief introduction, I will start the program with Professor Santanu Bandyopadhyay. He is currently Institute Chair, Professor, Department of Energy Science and Engineering at Indian Institute of Technology, Bombay, Mumbai. He is a blend of typically, I think, the specialty in energy because of his multidisciplinary background. He obtained BTech in Energy Engineering from IIT Kharagpur as a graduate student, which is associated with Electrical Engineering Department. Done the mechanical, done MTech and PhD in Energy System Engineering Center from IIT Bombay. Basically, MTech Energy System and Engineering is close to the mechanical department, and his PhD is close to the chemical engineering department. So he is having a background of electrical, being a graduate in energy, which is associated with electrical engineering department. Mechanical, master is related to the mechanical stream, and PhD from the chemical. So for the multidisciplinary engineering branch, he is the very right person, having a background of all these three important streams. His research interest includes process integration, pinch analysis, industrial energy conservation, modeling and simulation of energy system, design and optimization of renewable energy systems. Since 1994, Professor Santanu Bandyopadhyay has been associated with and contributed towards various developmental and industrial and research activities involving different structured approaches to process synthesis, energy integration and conservation, as well as renewable energy system design. Prior to joining IIT Bombay, he worked for Engineers India Limited, New Delhi. He was one of the section editor for Elsewhere Project, Encyclopedia of Sustainable Technologies. He is currently one of the editor-in-chief for Process Integration and Optimization for Sustainability, Springer Nature publication, as well as associate editor for Journal of Cleaner Production, Elsewhere, Clean Technology and Environmental Policy, Springer Nature, South African Journal of Chemical Engineering, Elsewhere, transcription of the Indian National Academy of Engineers, Springer Nature. He conducted a lot of continuous education programs for the working professionals from industry as well as academia. He's also written books as well as edited quite a good number of books. He's having the research papers in journals nationally and internationally well known, more than 250. He's having the citations more than 5,000. It's one of the work is cited related to the organic Rankine cycle analysis more than 300 times. With this renowned researcher as well as very good human being, it's a good combination. With this, I request Professor Santanu Bandyopadhyay sir to start his lecture. Please, sir.
Thank you, Mukund. Thank you very much for the kind introduction.
Sir, 1 minute before going for the lecture, I think we can conduct the poll to check the voice is audible or not, so that we can able to understand. Huh?
Yes.
Yeah, I will just launching the poll for the voice check. Please participate in that. This program is basically the pinch analysis, which is interdisciplinary lecture. So without any background, you can able to understand how the capability pinch analysis is having and how it is revolutionized the industry scenario, basically for the targeting of energy as well as water. It is also finding applications in others, but in a small span of hours. Other applications cannot be possible. Professor Bandopadhyay sir runs 5 days dedicated program on the pinch analysis also. So you will come to know about that. Around 60% people participated in this poll, and remaining please vote for this. 30 seconds I will keep it open, and then I will close this poll. Be fast, participate in this particular poll, and let us know that whether the audio speaker's voice is audible or not.
Yeah, good morning,
Now,
everyone. Please let us know whether you can hear me.
yes, please check the speaker's voice is audible or not. Around 60% people participated in the vote. Be fast. Yeah, I am closing this vote within a 10 seconds. Be fast, those who are remaining, participate in this poll. If you are not able to vote in this, minimize the screen and then again keep the screen back and then vote. Check your audio setting if any difficulty is there. I will close the poll now. Around 96% people says that you are audible, and 4% if you have any difficulty, please check the audio setting and back. I will hide the poll and hand over to the today's speaker, Professor Santanu sir. Sir, please.
Good morning. If there are people who cannot hear, can you quickly check your audio setting, whether is there any problem? Okay, let me do one thing. Let me turn off my webcam, because that might take the bandwidth. So I'll focus primarily on the talk today. And today I'll be talking about pinch analysis in textile industry, but I'm not really going to show you about applications of pinch in the textile industry in details, because as I came to know that most of you are not from the textile industry. So I'll try to skip that application portion, which I just quickly edited in between. And what I'll do is I'll try to focus in general on pinch, so that as an academic faculty, which is most of you are doing, you'll see how it can be applied, and what are the small adjustment can be made, and other different kind of applications can be done. And those who are from the textile industry, you can see another technique by which you can talk about energy and primarily water conservations. Yes. Okay. Now let's see what are the final results that has been put and in the literature. So by applications of pinch analysis. So in 1999, there is a study has been done in Portugal, which talks about 15% steam savings through pinch analysis. And in 2008, there is a study has conducted on 303 textile industries in Taiwan, and they have estimated a significant potential of energy conservation. Okay, you can see like 95 gigawatt hour of electricity, 23 million liter of fuel oil, and roughly 5,000 tons of coal. Okay, these are annual conservation potential, energy conservation potential that they have estimated. Similarly, there is a study has been done in a textile mill in Malaysia in 2002, which this is 16 to 50% operating cost reduction is possible. In 2001, there is a study has been completed, actually also implemented in Denmark, and they have reduced 40% of water with a 2 years payback period. So this seems to be the one of the places or one of the technologies which have been applied in the various textile industries all over the world. I'm not going to go on keeping the list of all the applications, but just to give you some highlights that it can identify a significant amount of energy and water conservations. However, I'll be focusing on the energy conservation part, and then I'll show you how the water conservation can also be done. So let's start with the design activity. Now, whenever we are going to design something, we are always going to focus on few things is the hierarchical analysis. That means the way we do the analysis one by one. Typically for many complicated things, it is not possible to do everything together. However, there are different approaches. So we follow kind of an hierarchical analysis. And whenever there is a problem that we have to solve in real life or in our professional life or everywhere, we try to see the problems and put it how we are going to solve it. Is the computer is going to give us the solution, or we are going to find out a solution for it? So whether it's an interactive or automatic. Second thing is we also look at the problems and try to see whether we can write a more logical equivalence of that as a logical representations with a qualitative or a quantitative. So if it is a quantitative mathematical model, then it goes in one, or if it is not a really mathematical one, so we are going with the gut feelings, and that can be or descriptive kind of things, it will be a qualitative models. So models and the solution technique that we are looking for, we can divide the entire analysis into 4 quadrants. The first quadrant, where you have typically qualitative models with interactive, or the designer is going to take the call, that's our heuristics rules. Okay, there are different heuristics rules are there. Now, if you look at the second quadrant, where there are qualitative rules, however, the computer is going to generate, it comes out, sorry, it comes out to be knowledge-based systems. This is now getting extremely popular with the coming of the artificial intelligence and the machine learning processes. Okay. Then there are quantitative methods with automatic approach, which comes out to be the optimization methods, which are also becoming extremely popular. And academicians typically prefer this optimization approach, write down mathematical programming, stochastic search methods, and so on and so forth. And the fourth quadrant, where you have mathematical models, but the designer is going to take a call, we have thermodynamic methods. Pinch analysis is just one of them. Today we call this third quadrant and the fourth quadrant, that is combination of thermodynamic methods and optimization methods, as process integration and optimization. So in a sense, pinch analysis is a part of process integration and optimization. Let's look at what is process integration. This is the definition given by Professor Truls Gunderson. He says systematic and general methods for designing integrated production system, ranging from individual processes to total sites, with special emphasis on the efficient use of energy and reducing environmental effect. Energy, environment is understood, but remember a few things. It says general methods. So that means not a single method. There are multiple methods are there under its purview. And it says designing integrated production system. It does not say what production. So it can be any kind of production system which comes into its command. Later on, we'll see some of the places where this techniques are applied. Now, what are the objectives of such kind of a study? The objectives are to minimize the total cost, or to increase the plant capacity, to reduce the operating problems during the startup and shutdown, increase the plant controllability so that it can take care of the topological related problems. You can increase the flexibility. You can minimize the undesirable emissions, and finally, we all aim for a sustainable development. So this is the way the development has happened. These are the few objectives that has been taken and answered, not all of them completely, but partially. And that's the research part of it, while we are developing and try to address many such issues. Let's look at what happens in the different two categories. So one of the category that is of process integration is the mathematical optimization, which comes from the third quadrant. So one good thing is, or like the major good point is, it's a preferred for if the problem is complex, multiple contaminants, controllability, flexibility, cost optimality, and all such of complex things, topological optimizations, uncertainties. If you want to consider all of them, mathematical optimization is better. However, your model has to be better and representative. It's a very good synthesis tool in handling complex systems with complex constraints. However, it has problems. The problems are there are combinatorial explosion and local optimality. What do you mean by combinatorial explosion? Many of the variables will be discrete, and then you have to look at different discrete points and evaluate whether they are good or bad, whether they are local optima or not. And if there are many number of or large number of discrete variables are there, then it happens the space is really large, and that it leads to a combinatorial explosion. That means the amount of search space that you have to search is really large. Many cases, the mathematical optimization programs that we have may get stuck in the local optimality, and it's difficult to find out the global optimality. So nowadays there are techniques, heuristics based techniques or meta heuristics techniques or even evolutionary techniques, they are all equivalent, are coming up, like genetic algorithms and so that to solve some of the real complex problems. It does not provide a good insight to the process designer during network synthesis or during the detailed engineering activities. So you had done a mathematical things and you got an optimization result, but sometimes you are not sure about what to do with that special, because there are certain things are not acceptable. Some mathematical solutions may not be acceptable to you. You want to go for the second best. How do you go for it? The second best solutions have never been reported. So it's become very difficult. Again, you have to run it, you have to look for it and things like that. If something goes wrong, you are not sure what exactly went wrong. You might have done a particular portion, you have written down one equation wrongly, the complete solution came wrong. You identify that there is something wrong with that, but you don't know what exactly went wrong. It's become difficult because it's become more kind of a black box approach. And many cases, there are simple algorithms can be done to solve a problem. So let me give you a simple example for the last point. Suppose I ask you to optimize a function y equals to x square. How will you do? The simple thing is differentiate. You'll get 2x equate to 0, x equals to 0. So that's a stationary point. Now you double differentiate, you'll get 2, it's positive. So hence x is a local minima for this particular function, and we know that the function is convex, so it is a global minima at x equals to 0. Now that's a simple classical approach. You can solve many problems with that. However, there is a very special structure of this particular problem, and that special structure is I can use that and solve it in one line, that x is a real number. So x square has to be always non-negative. Hence, the global minima can be only at x equals to 0 when x square equals to 0. Now, this particular, the second one is much simple. It gives you more understanding of the functions and behavior. However, it cannot be applied to generic problems. So mathematical optimizations are in some sense look at generic way of solving a problem. And on the other hand, this particular kind of, there are special techniques has been developed to solve some special problems very efficiently. Okay, we'll discuss during the pinch what exactly happens and what do I mean by this. If I look at the fourth quadrant, that is the thermodynamic based approaches or conceptual approaches, it helps you in understanding the physical insight through a graphical representation and simplified calculations. So there will be two things. One is there is a representation through graph by which we can understand better. Most of you are engineers, And as an engineer, you can see that we prefer to have a figure to represent everything rather than just equations or things like that. And that is one of the acceptability point, green points for this pinch analysis. There are simplified calculation procedures. We'll come and go through quickly because there is not too much time to take you through in details. There are efficient calculation procedures due to spatial structure, as I given that example of y equals to x square. We extract such kind of informations and go ahead. And by the way, if you have any questions in between, you can write in the chat window. I'll just look at it and answer. Then it's also use one other important things, which is setting a target before actually solving it. So it doesn't say what exactly will be the solution of the problem, but it will simply say this is the objective function, and it can be done very efficiently. And that's the way industry is extremely helpful. They know that where to stop. So suppose the target is 100 and you have reached up to 95, you know there is no point in putting too much amount of effort or time, and you can go ahead with that 95. Maybe next time you can improve further. But if you are at 75, you know that okay, you are too much away, you should look for the actual solution. So that way it helps the industry, and that's why the industry has taken this pinch analysis in a big way. It also provides a graphical representation, okay, and that has some kind of a control and the complete control by the designers. However, it is applicable to only simple systems with simple constraints. So one of the research agenda that we do is try to extend it for a complex systems with complex constraints and see how much we can retain the advantages of pinch with its application to much more complex systems. Okay. So let's start with the classical example of heat exchanger network. What do you mean by heat exchanger network? That suppose there is a process we are talking about, you can take textile or any other industries. There will be some streams which will be hot streams. That means their temperature has to be reduced. They have some amount of heat available which has to be taken. And there are some cold streams where heat has to be transferred and its temperature has to be increased. So we'll define the hot stream as the streams whose temperature has to be reduced and not based on its temperature itself. It's a direction of temperature change. Cold streams are those streams whose temperature has to be increased, and hot streams are the streams whose temperature has to be reduced. Okay, so we can have a cold stream at 1200 degrees centigrade if we have to increase its temperature to 1300 degrees centigrade, say for example. So it will be still a cold stream, we'll call it. We call, because some of you are not from mechanical engineering or chemical engineering background, so I just thought of repeating it. And if we can also have a hot streams at minus 100 degrees centigrade if we have to reduce its temperature to minus 150. So we are going to look at the direction of temperature change and not the temperature itself. So hot streams will have some heat which has to be removed. Cold streams require some heat, so we have to provide it. One way we can provide it is from the heat from the hot stream to the cold stream. And in industry, there may be many such streams, may not be one exchanger. Heat exchanger is sufficient. We have many such heat exchangers and we call it a heat exchanger network. This is the problem that we are going to look at because this is where the pinch analysis was originally started. So let's start with the problem definition of heat exchanger network. So you are given a set of process streams, hot process streams, its temperatures, mass flow rate, and heat capacity. Similarly, a set of cold process streams. We know its temperatures, we know its mass flow rates, we also know its heat capacity. We look at some external utilities to provide heat to the cold streams or to take away some of the heats from the hot streams. We call them hot utility and cold utility respectively. And their temperature is known. We have to find out how much. That is our one of the objectives. Heat exchanger data cost data are known, then our objective is essentially to find out a network of heat exchangers such that the annualized investment and operating cost, or the total annualized cost, or the total life cycle cost is minimum. So we want to find out an economic minimum for given this. That's the problem definition. Now let's look at quickly some history. Historically, what happened? So 1944, there was the first paper appeared in the open literature by a person called Parikh. It's just 1.5 page paper, and he didn't call it heat exchanger network. He called that time bridges of heat exchanger. Then the next one came in 1961. Professor Westerburg published a paper on the mathematical programming of heat exchanger network. And then Professor Rudd published in 1968 an extremely important principle called decomposition principle. That time he said, like, if the problem become too complex, do not try to solve the entirely, and then solve in parts. And that's what we do throughout our life. As an engineer, sometimes the problem become too difficult, we try to solve in small parts. Then there is an interesting thing happened in 1971. There's a person called Homan who has done his PhD, and there he introduces the concept like composite curves, minimum utility requirement, minimum number of heat exchangers, and things like that. And the terminology will not be very clear to you now, but I'll soon it will become. This is the first work of Pinch. However, he tried to publish this in a very prestigious journal, and it was turned down twice. Today, when we look back, a technology that has been used by many people, the analysis tool which has been applied by so many industries and so many industrial fronts, why it was rejected? Probably if I look back, we can look at in two ways. One is, now look at the year 1971. 1971, people are not talking about energy and conservation of energy. 1973-74, first oil shock came, and 78-79, second oil shock came. So people started realizing that energy is finite, we have to conserve it. So that time people are not talking about, and somebody comes and says, this is the way you can conserve energy. Nobody was interested in listening to. Then the second one is, towards the end of 60s, people started applying computers everywhere. And in 71, this person, Homan, done a research where he says the computer is not required. You can simply calculate by some simple calculations and get a solution. People are not really appreciative of it. Okay. So probably because of these two reasons, his paper got rejected. In 1978, two independent papers published, one by a person called Bodolenov with his supervisor, Professor Flower, and another is Dr. Umeda and his colleagues from an industry, that is Chiyoda Incorporation, Japan. They published a paper and said how the heat can be recovered through this pinch analysis. And today we consider these two papers as the starting points for pinch analysis. Remember that very interesting thing. One paper came from industry, another paper came from academia. Then what happens in academia, all the papers are available, open source, but industry has their own constraints. They cannot publish everything. So many of the work done in industry are not published. However, we know some of the people, and including Chiyoda Incorporation, they are doing great jobs, and they are also taking this pinch analysis forward. Then there is an interesting work happened in 1983. Then Lunov has become a professor, and his students, Heinmarch, both of them published a method called pinch design method, by which they said like that energy targets can always be fulfilled. that it's not purely a target. It's not something that all of us wrote as an essay in class 8, what is our aim in life, and we just don't know what is going to happen. We just wrote. Okay. Similarly, here it's a science subject and not purely an aspiration, and that can be essentially achieved, and that's what they have demonstrated through a method. And in 2001, Professor Sahinides and his students, Furman, have published a paper where they have shown that this problem is very difficult, especially for the industrial scale. If you want to write an algorithm to solve optimization algorithm, then this cannot be a polynomial time algorithm. It will be an NP hard non-polynomial problem, and so you cannot really solve and say that this is the solution, because MINL, this will come out to a mixed integer nonlinear programming model, one of the most difficult things, and we don't have mathematical knowledge to say that we'll find out a local optima. In fact, we just don't know even after running a code whether you got even an optimal solution or even any feasible solution. So those kind of problems are there. And in fact, a few years back, one of our senior published a papers in a conference where he showed over the last 20 years, one of the simple heat exchanger problem, heat exchanger optimization problem or heat exchanger network problem has been worked by some 10 different groups with 10 different formulations, and all 10 groups has proposed 10 different solutions. So you're not sure. All of them use mathematical optimizations. All of them use the same software, okay, called GAMS, but different formulation and got different answers. So that's the kind of complexity. So that means we have to go back and use Professor Rudd's principle and divide the problem into smaller zones and start solving it. And that's what we are going to see in the next few minutes. Let's start seeing a very simple problem. This example, there is a stream which is coming at let me put the highlighter or the spotlight. So there is a stream which is C3, which is coming at 20 degree, goes heated up to 155, goes to a reactor. After reaction, it comes out at 175. It is cooled to 45 degrees centigrade, goes to a distillation column. From the top of the distillation column, the distillate comes out at 40 degree. It is heated up to 112 degree and goes to another process beyond the battery limit of this particular process. So we are not interested. However, 112 we have to always meet. The bottoms of the distillation columns comes at 125 degrees centigrade. It's cooled to 65 and goes to a storage tank. So you can see that the stream H1, which starts from 175, we have to cool to 45. It's a hot stream. H2, it starts from 125, goes to 65. It's another hot stream. That's why I call it H1 and H2. C3 starts at 20, goes to 155, increase in temperature. It's a cold stream, C3. And 40 is increased to 112. So that's another cold stream, C4. So you have some 2 hot streams and 2 cold streams, simple problems. And I have taken the problem from Professor Shenoy's book, and just to demonstrate the entire concept. Now let's try to see what is the duty or MCP. So all of you probably remember that the duty of a stream Q can be represented as MCP, change in temperature. M is the mass flow rate, CP is the heat capacity. So and in our case, we just calculate the MCP together. Now let's look at, it starts from 20, goes to 150. These are the exchanger 1, 3, 2, and 4. This exchanger duty is 1300 kilowatt. H1 is another exchanger whose duty is 1400. Total duty or the heat required for C3 is 1300 plus 1400, that is 2700. Okay. Now H1 loses 1300 unit of heat and it reaches 45. C4 starts from 40, goes to 102, and there is an heat exchanger where it gains 1080 amount of kilowatt of heat. and H2 starts from 125 goes to 65. It has two heat exchanger associated. One is 1080, another is 1320. Total is 2400 kilowatt of heat. Okay, now this one already have some heat exchanger exchanging heat between H1 and C3 and also H2 and C4, that exchanger 2. Exchanger 1 is this required steam for heating the cold stream from 85 to 155, and this hot stream from 98 is cooled to 65 using cooling water. CW stands for cooling water. Now the question is, can we do better? Can we conserve more energy? Can we reduce our steam requirement? And so on and so forth. So let's look at the simple all the streams and not look at all the processes, because it should not clutter our mind. And if I look at, there are 4 exchangers, heat exchangers. One is exchanger 1 between steam and C3. Exchanger 2 and 3 are process to process heat recovery units, and exchanger 4 is basically a cooling water unit. Now we have to calculate the MCP using the formula Q equals to MCP dt. Now let's look at H1. It starts at 175, goes to 45, and it through only one exchanges 1300. That means the total change in duty Q is 1300, and change in temperature is 175 minus 45 is 130. So 1300 divided by 130 is 10. So we can write down the MCP of H1 is 10. We can calculate the MCP of H2 similarly, 125 to 65, and you can see the total duty 1080 plus 1320, that is 2400 divided by 60. What is the number? 40. Now can you calculate and say what is the MCP for C3 and C4? You please type it out. I'll just wait. Please type your numbers in the chat window. Let's look at C3. There are 2 exchangers. Duties are 1400, 1300. Total duty is 2700. Temperature change is 155 minus 20 is 135. 2700 divided by 135. How much are they? You can use your mobile calculators in your mobile phone as well. No answer? Are
Sir,
you
they
online?
cannot write down in a chat box, but they can write down in the questions. C3, Siddhant Patel is saying that C4 15.
Right.
Taruna Jain says that 20 and 15 for C3 and C4.
I see
Siddhant,
only one message from Sanjay Patel.
yes, actually, sir, he can only give the message to you. This question box is not accessible to you.
Okay, it is not accessible to me. Fine. Okay, thank you everybody. Yes, the answers are 20 and 15. That's fine. So now we are going to look at this, and if you look at the steam requirement is 1400. Okay, so I'll just go to the pen mode. This is our steam requirement and this is our cooling water requirement. Our objective is, can we reduce it further? Can we do some kind of energy conservation? Can we, and this will in turns also will require some amount of cost cutting. Okay, let me erase this. Okay. Now let's start with the first thermodynamic laws of thermodynamics. So if we look at the enthalpy changes, you can find out that H1, I'll go back, H1, the total duty is 1300, H2 is 1080 plus 1320, that is 2400. So H1 has a duty of 1300 and H2 has the duty of 2400. Total duty is 3700. That much amount of heat is available. And cold stream C3 requires 2700 kilowatt of heat and C4 requires 1080 kilowatt of heat. Total requirement is 3780. Now, suppose I do not want to do any integration. What is the maximum limit? Okay, we can find out the maximum limit saying that, okay, see all the heat requirement out here can come from the cold utility. Okay, so that means this is the heat available in the hot streams. I can pass it to a cold utility, and this is the total heat required for the cold stream, which can come from the hot utility. So steam requirement is 3780 and cooling water requirement is 3700. Obviously that's not an acceptable solution because our present solution is much better than that, but this gives us a limit. Okay, now the question comes is, can we take the advantages of heat that is available at some hot streams and can we pass it through an exchanger or network of exchangers or many heat exchangers? What can we do? So that's what we are going to look next. So let's look at the first law of thermodynamics, what it says. It simply says that the heat available in the hot process streams and the hot utilities must be equals to heat required by the cold process streams and the cold utilities. That means energy is conserved. Whatever heat is coming in must be that same amount of energy or the heat goes out. So if I write down in symbolic manner, what we can do? We can say the total heat available in the hot streams and total amount of heat which is available in the hot streams and the heat which we are going to take from the hot utility must be equals to the stream heat required in the cold streams as well as the cold utility. So now we can rearrange this and we can write down QHU minus QCU equals to 80. What could be the solution of this? So one simple solution is, we can say that I need only 80 amount of hot utility and 0 amount of cold utility, right? That's absolutely minimum from the first law. But probably this is not going to be an acceptable solution. Why? Because something known as the second law of thermodynamics. And what does it say? So it says the heat cannot be transferred from any temperature to any temperature, any hot stream to any cold streams. It has to be transferred from high temperature to low temperature. That means there has to be a temperature difference. The delta T, the temperature difference, should be greater than 0. Then only we can transfer the heat from one stream to the other stream. Now, how do we take care of that? So that is what we are going to look at. So we are basically taking this approach that we are going to add streams to produce one hot streams and one cold streams, which will have the thermodynamic characteristics We are not talking about the mixing of the stream, but kind of an adding thermodynamic space, so that we can transfer the heat from one hot stream to another cold streams and see how it can be done, subject to the second law of thermodynamics, that the temperature difference has to be greater than 0 for transfer of heat. Now let's start with this in a graphical way. So if you remember the stream data, we have H1, which starts from 175, goes to 45, and with a heat duty of 1300. I represent this out here. So what is happening again? It starts from here, that is 175. It ends out here at 45 degrees centigrade. So it's basically, this is the direction of this particular streams, and in such a way that this difference is 1300. Okay, that's the way we have written down. Now so what is happening now? Let's look at, can I take these streams and make a vertical movement? Is it possible to make the vertical movement? Can I draw from here to here? The answer is no, because these temperatures are fixed. 175 and 45 are given temperatures, so that is fixed. Okay, so we cannot do this vertical movement. However, we are allowed to do horizontal movement. I can simply draw it from here to here, as long as this to this difference is 1300, the same difference as this. It doesn't matter where we are going to start. So your y-axis is a kind of fixed one, but x-axis is relative. Only we are talking about the differences, and that's what we are going to exploit. So we can plot the next stream H2, which starts from 125 degrees centigrade, goes to 65 degrees centigrade, and with a degree of the heat availability of 2400 units of heat. Now we can present it. Now how can I add that? So we are going to add these two streams in a thermodynamic way, and we call it hot composite curve. Remember, this composite curve that we are going to generate is a pseudo one. It does not exist in real life. It only exists in a thermodynamic scale. So it represents the heat availability as a function of temperature. So how do you do it? So let me start with the final result. The final result will be something like that. So the below portion, let me see the pen color to change it to some. Okay. This is the portion. Look at, from 45 to 65, entire heat is available from H1 only. So this is the same as that. Now here, between 125 to 65, heat is available from here as well as from here. I add it, I'll get this 6. And again, from 175 to 125, heat is available only from H1, and this represents whatever the heat is available from H1. Okay, so let me repeat once that whenever we are adding these two streams H1 and H2, we are simply finding out for every temperature interval how much it is available, and that's what we are going to represent. From 45 to 65, heat is coming from H1 only. From 65 to 125, heat is basically available from H1 and H2. I'll just simply add it up and say this is the amount of heat is available. And 125 to 175, heat is available again from H1. So now we'll get something known as the hot composite curve, or HCC, which represents the heat availability as a function of temperature. Again, this does not exist in reality. It's only exists in thermodynamic space. We can do the same thing for cold stream C3 and C4. We can add and we can get a cold composite curve. Now, what is happening? Hot composite curve is basically saying the heat availability, and heat can be transferred lower temperature. Cold composite curve is a heat requirement as a function of temperature, and it has to be supplied from higher temperature. Let's put them together in the same graph. Now, in this graph, what happens is, this is our hot composite curve where the heat is available as a function of temperature. It can only give you some lower temperature. This is the cold composite curve, which requires heat from some high temperature. Now, I have put them very much apart. That means all this heat has to be taken care by some cooling water, and this heat has to be supplied by some steam. So that's a maximum limit. Makes no sense. Let's put together. Now, once we start putting together, then we can bring them very close by. It may happen that they might touch or overlap. Okay. If there is an intersection point, that means heat is transferred from low temperature to high temperature, which is not allowed. We should have some temperature difference. Even if they touch, then what happens is your heat exchanger area goes to infinity, and then the capital cost requirement goes to infinity. So that means we need some temperature difference, which is positive number and not zero. Okay. So that means we have to place this hot composite curve and a cold composite curve in such a way that there is some temperature difference. And if I do so, I'll get this. Your red curve is the hot composite curve. This is your hot composite curve. This is your cold composite curve. And the point they are close by is basically the pinch point. The portions of the overlap, hot composite curve passing the heat to the cold composite curve, that is the process to process heat recovery. Now look at here. We have a cold streams, but there is no heat coming from the hot stream. Nothing is present. So I have to supply externally. That is the minimum hot utility requirement. And here I have some heat available, but there is no taker internally. That means I have to throw it out. So this is the minimum cold utility requirement. So now this process can be put graphically. Both the composite curve has been put, hot composite curve and the cold composite curve, and we have both of them together. We can find out what is the process to process heat recovery, what is the minimum hot utility requirement, what is the minimum cold utility requirement, and that we can solve this problem graphically. And completely we can see what is happening. I'll take a pause, and if you have any question, please put in the question window so that I can reply to you.
Sir, there is no question as such.
Okay, fine. Thank you. So if this curve is clear, sorry, if this curve is clear, we have actually understood what is pinch analysis. Pinch analysis is basically to identify the pinch point and to calculate the minimum hot and minimum cold utility. But you might ask the question is, how do I do this shifting? How do I actually calculate? How can I plot this graph and then study it exactly? It becomes very difficult. So we might do some kind of a simple algebraic technique. So that's the question: can we target the minimum energy requirements in algebraic way? Yes, there is some small paper has been published in 2010, okay, with one of my students, and that talks about an algebraic way. But what we do is we'll go through those calculations quickly so that you can see it is what is happening. We are going to make a kind of a transformation. Okay, we call it shifting. What we do is all temperature associated with hot streams will reduce their temperature by half delta T min, and all the temperature associated with the cold streams will increase by half delta T min. Remember, we are doing a transformation for mathematical sake, and we should put it back to understand, do the inverse transformation to understand the physical meanings of these results. Okay, so let's start with that algorithm. And it essentially, there is a kind of model which goes into these calculations. That means there is a stream. We can imagine that there is a stream which comes at Tik, okay, through an pseudo exchangers and go at T naught. Then I can say that there is some kind of a thermal oil is coming at just half delta T below, and here it is just going out at half delta T below, and then it is, this can be all mixed and all. This is a thermodynamic model, goes behind our calculations, but you need not focus on that. You can only focus on the way we are calculating this. Okay, so I just wrote down these things. This is from that paper. You can look that paper and download. This is an algorithm, so I'll just skip it. I'll come here and say, now first thing we are going to do the transformation of the temperatures. Our delta T min is 20 degree. Why 20 degree? Because half delta T min is 10. It is easy to calculate. Okay, there is nothing so sacrosanct about this, but however, I'll talk about little bit how to choose the delta T min. Our first step is to reduce all the hot stream temperatures by half delta T min, that is 10 degree, and all the temperature associated with the cold streams up by 10 degrees centigrade. And then we write down separately, this side is the inlet side, this is the inlet side, I will write down here, and this is the outlet side, we'll write down here. Okay, and that's the way we are going to look at it. Okay, the first one is, what should be here? See, look at H1, the inlet temperature is 175. We have to reduce it by half delta T min, that is 10. So it's become 165. H2 will become 125 minus 10. That will be 150. C3 will become similarly 20 plus 10. That is 30. And C4 will become 50. Similarly, if you look at the outlet side, we have 35, 55, 165 and 122. Okay, and I have written this MCP both the cases. Now that's the first step. Second step, this is the table we have generated. We are going to go through an algorithm. First step of the algorithm is to write down the temperatures in descending order, and we need not repeat if any temperature comes twice. So now, what is the highest temperature from here? It is 165, right? So we'll write down first 165. Next, if I look at all these numbers, next number you can find out is 122, just associated with C4. So we'll write down 122. Next, 115. Then 55. Then 50, 35 and 30. Okay, so we have written down the temperatures in descending order. Next step, we have to write down the MCPs, but here we take an sign convention. We'll take the inlet side as positive and outlet side or the demand side as negative. And for any temperature which is repeated many places, we'll take all the MCPs, add them and put it with this particular sign convention. Look at 165 is there in inlet as well as outlet. Inlet is 10, outlet is 20, but our sign convention says inlet is positive, outlet is negative. So we'll add 10 plus minus 20. What will get? Minus 10. So for 165, we'll write down minus 10. What will happen to 122? It will in the outlet side, so it will become minus 15. 115, it's in the inlet side, so it will become plus 40. 55 will become minus 40. 50 will become plus 15. 35 will become minus 10 and 30 will become minus 20. Sorry, plus 20 because this is in the inlet side. Okay. Now, once you have written down the MCPs, then we do something known as a cascading. What is cascading? Cascading is, we'll write down these numbers here as minus 10 and then I'll add these two diagonally and write it here. This will become minus 25. Then I'll add this to minus 25 plus 40. This will become 15, and so on and so forth. Okay, so let me remove all of them. So the first entry will be minus 10. Then next entry will be minus 25. Then it will become 15. 15 plus minus 40 is minus 25 again. Then minus 25 plus 15 will become minus 10. Minus 10 minus 10 will become minus 20. Minus 20 plus 20 will become 0. So if you do through this algorithm, this will always become 0. Then what happens in enthalpy? We'll calculate. First one we'll write down as 0. Then next onwards, 165 minus 122, that is these two temperature difference multiplied by this cascaded flow, and we'll write down here. Okay. So the first entry will become, then let me go through the pen and write it down. This we'll write down as a 0, arbitrary one. 165 minus 122 is how much? 43. 43 into minus 10. This will become minus 430. What will be the next? We can carry again 122 minus 115 multiplied by minus 25. We can write down here. So let's proceed with the algorithm. So the first entry is 0. Next entry is 165 minus 122 into minus 10 will be minus 430. Then 122 minus 115 is 7 into minus 25 will become minus 175. Then 60 minus 115 minus 55 is 60 into 15 is 900, and we can continue the next three numbers. Probably at this time I'll just take a stop, and again I'll ask you, do you have any question?
Sir, you can able to see the question box also over there, sir. Now.
Within the chart?
No, sir. Questions. Just like a chat, there is a question.
Okay.
So if any response is there, you will get from there.
Okay, just a minute. It shows very small, so let me.
Yeah, you can take it out.
Whether
you can unmute and take it out.
I cannot. Seems to be like I'm not really. Acha. Okay, I can see here. I don't understand the question. Acha, this is probably done now. Okay, I don't see any questions related with whatever we have done so far. Okay, so I'll continue.
Balaji Dhokte is saying that pinch temperature in the optimization, it is compulsory to be 9 to 10 degree.
Okay, I'll come back to that point. This is not a pinch temperature. This is just the temperature difference. Pinch temperature is the temperature where this pinch occurs. Okay, there are two different things. We'll come back to it soon. Okay, just allow me to explain, go through, and again I'll take a pause after completing this algorithm. So what we have done is basically we have written down these algorithms, and I'll continue mechanically. I'll just do another cascading. What does that mean? It means again the same way. I'll write down this number. First start with 0, then diagonally add 0 with minus 430. It will become minus 430. I'll add minus 430 with minus 175. I'll get minus 605. I'll add minus 605 with 900. Okay, I'll get again 295. 295 I'll add with minus 125. That means 170. Okay, and I'll carry on. I'll get finally the minus 80. Now, what does we have done? We are basically this cascading. What we have done here is basically transferring heat from high temperature to low temperature. But what does this positive and negative means? Positive means there is a heat availability. Negative means it's heat requirement. So I can transfer positive heat, but I cannot transfer a negative heat. That means heat demand required at 100, I transfer it to 900 degree. That's not possible because it has to come from somewhere higher temperature. That means this cascade table, the last one that we have completed, should not have any negative numbers. It can have only positive numbers. That means instead of starting from 0, we should have started with some other number such that this will become all non-negative. How do you do that? We can only do it if we, instead of 0, if you have started with a number which is the lowest in this column. That means 605. So this is minus 605. If we had started with 605, this should have been no negative number. So that means now after doing the cascading, we find out the minimum number, or in the typical Indian non-grammatically correct way of spelling is the lowest, or we should say the highest negative number. But highest negative number or maximum negative number makes no sense, but we can understand that we are talking about the lowest number. Lowest number in this column is minus 605. We'll subtract 605 from all of them, and no more cascading, just 605 will be added to that number, or minus 605 will be subtracted. So 0 plus 605, then the last column of the final column we are writing will be 605. Then 605 plus minus 430 will become 175. Then 605 plus minus 605 will become 0, and next number will be 90, and will continue, and finally you will get 525. Okay, now this is what we have done. We have solved essentially the problem. We have the results in front of us and we have to interpret them. What is the interpretation? What are the important ones? So finally we are going to look at all these three: minimum hot utility requirement, minimum cold utility requirement, and the pinch temperature. Right? Remember, delta T mean is not the pinch temperature. However, there will be some pinch temperature where the temperatures difference is actually 20 degree. Now, the first thing that we are going to look at is the top of this final column, 605. Okay, that is very important because that suggests our minimum hot utility requirement. Next number is the lowest of this column, okay, or the last entry of this column, that is 525. That is the minimum cold utility requirement. And our pinch is where they have become 0. Okay, now 0 it corresponds to 112. So if I look at this, this is the 0 and this corresponds to 115. But what is this 115? 115 is basically a shifted temperature. So, and what kind of shifting we have done? Hot streams are shifted down by 10 and cold stream are shifted up by 10. So that means what will be the corresponding pinch temperature? Hot stream should be 115 plus 10, inverse transformation, that means 125, and 115 minus 10 will be the cold stream temperature, that will be 105. So our stream temperature will be 125 and 105. So this is the final result that we have got. Now here I'll just highlight quickly what we have done is we have done an optimization problem because we are finding out minimum hot and minimum cold utilities. This is a linear programming problems. It can be solved using simplex. However, we have solved using a graphical method as well as an algebraic way. Okay, so graphically we could see what is happening. and algebraic way we can see how to proceed. And it's a very simple, we have not invoked anything like simplex, and if you remember the complexity of those, we have just simply solved it. Okay. Now, so what is the physical significance? One says the pinch divides the process into two thermodynamically separate regions. One is high temperature heat sink where heat is required, another is low temperature heat source. And this pinch temperature is the temperature of the hot and cold stream where they are just separated by this delta T min. That helps us in doing certain other things. That most important things are, we should not transfer any heat across the pinch. Okay. Then there should not be any cold utility above the pinch. There should not be any hot utility below the pinch. If you violate any of them, both hot utility and cold utility will be increased simultaneously. Remember, hot utility requirement and cold utility requirement, their difference is fixed. And if you remember from the first law, it says 80. Okay, you can see that number also, you got it. 605 minus 525 is exactly 80, right? So that has to be there. So that means there will be double penalty or double reward. Okay, that's what we have to look at. And pinch point is the bottleneck. We cannot do better unless we change the delta T mean. Now the question is, if I plot only the first column but the second column, it's known as a grand composite curve, and it also gives us the same information that this difference is 605 as the hot utility requirement, and this is our cold utility requirement. From here to here is our cold utility requirement. Okay, so we can find that, and this is the pinch point where they have touched. Okay, this gives us much more ideas about how to do it, and we can do a lot more calculations. Anyway, we are not going to do anything at present because it will take too much time, and the focus is just not pinch, other courses as well, but I'll just show you what is the idea. The other things we can do, this is about the energy. We can also apply this kind of things through a graphical thing, graph theory, and we can calculate the number of heat exchangers. I'll now go a little fast because I know that you people are all hungry and I have to also finish so that I can take some of your questions if they are there. We can calculate the number of exchangers. We can also calculate the area required. So in some sense, we can start with the stream data. We can start with the stream data. We can do composite curves. We can do energy targets. From this energy and utility targets, we can get operating cost. We can do something like area and the unit or the heat exchanger, number of heat exchanger targets, and from there we can get the capital cost. And we can add them, and we can say that this is our total annualized cost. And we can vary the delta T mean to find out what delta T mean this will get an optimum result. So typically it's become very difficult in industrial problems. However, sometimes we can do it, or many times industry also use certain thumb rules. Thumb rules are, if you are transferring heat between what kind of streams, if both of them are gaseous, your delta T mean will be high, typically in the range of 40 to 50. If both of them are liquid, it will be in the range of 10 to 15. If one of them is condensing or they are refrigeration steam, we go as low as even 3 or 4. Okay, so it depends on the application to applications, and we can do accordingly. Now, so we'll come back and quickly go through some of the application concept. That can we generalize this concept and go ahead. And this is one of the statement given by Professor Richard Dawkins in his book Blind Watchmaker. He says some of the greatest advances in science has come about because some clever person spotted an analogy between a subject that was already understood and another still mysterious subject. We are all inspired by this, and in one of the way is we learn from some known things and start applying there. So heat, if we understand, then we start applying to others. So the way we look at the pinch is it talks about some generalized definition, flows, qualities. It looks at thermodynamics, conservation relations, some phenomenological relations, and then it finally sets some targets. So it's prediction of the optimum performance prior to the real synthesis and detailed design approaches. And this is extremely helpful. It can say, instead of many cases it says 5% energy conservation, then it can say in the first year you can conserve total of 22% and no further. Okay, so that gives you how much to achieve and what is possible to achieve. So I'll just skip this. I'll just go to the typical sourcing problems, the way we look at in pinch analysis. We say there are some sources which comes with some flow and a quality. So in the previous example, you can say flow is heat and quality is the temperature. There are some demands which requires heat at certain temperatures or some flows at some qualities. We try to transfer from the sources to the demands such that the source quality is better than the demand quality. But sometimes it is not possible. Then we need an external things we call resource with certain quality, much better than all the demand, so that we can transfer them. And some sources, some flows will be remain because we may not be able to use it. We'll transfer it something known as another demand called waste, which goes out of the system. Our objective in pinch is we try to minimize this resource requirement. If I write down the mathematical equations, then it comes out to be some kind of, we want to minimize the resource subject to the flow balance at sources, flow balance at demands, and quality load balance at the demands as well. So it's become a linear programming problem. Okay, and that's what we have solved. Okay, so there are many methods, approaches. One is known as a limiting composite curve, where we try to find out what is the minimum resource. So for such kind of a problem, we can find out the source composite curves, where we can find out what is the minimum waste, or we can put something like a composite curves and try to find out both resource and waste together. These are the three most popular graphical tools and associated with their algebraic techniques. However, you'll not go into the details. Okay, if you are interested, you can always write to me. I'll send you the references. It has been applied for hydrogen recovery in refineries. It has been applied for nitrogen recovery in many coating industries and drying processes, solvent recoveries in degreasing plants, okay, water recovery in many places, including the textile industries, which you started with. Okay, it has been applied to isolated energy systems like the solar thermal, solar wind, wind, okay, and their combinations. How do you find out? It has been applied to financial domains, where there are projects you have to have different places to get money, and you can have again a source composite, sink composite, or demand composite, and then you try to match them, which project to fund, which not to fund, and things like that. Sometimes the projects have additional complexity that either you have to completely do that project or you don't do. Okay, and those kind of things introduces discrete variables called binary variables. Then it can be done through a combination of pinch analysis with branch and bound, and a hybrid technique had been developed. It has been applied to healthcare system. This is equivalent to the grand composite curve that I have shown you earlier quickly. Here also you can identify the pinch, we can find out where the beds are available, where the government should start focusing the development, how to do it, okay, what kind of changes in the scenario can make the overall system good. It has been applied to with uncertainties. How do you solve these problems with uncertainties? It has been done with multiple objective functions, like it has applied for the energy sectors for India, and shown there are different combination of the solutions. One look at the capital cost, another look at water footprint. So this solution has lowest amount of capital cost, whether this solution has the lowest water footprint, highest capital. Maybe a combination of them will be good, and this is known as a Pareto optimal front. Such kind of plots can be also generated. It has been applied to various things like heat integration, we just seen, mass integration, recycle resources, cogeneration system, carbon constant planning, and so on and so forth. Just to give you some history, this in 1970s, this is the picture of Professor Budolenov, and he is one of the major person introduces pinch and done a lot of work. Then this is Budolenov's colleague, Professor Robin Smith. He introduces the batch process and water minimization or water pinch. Next person is Professor L. Halwagi. He introduces the mass exchanger network and property integrations. He's from US. Then these two are very good colleagues of mine, Professor Dominic Fu and Professor Raymond Tan, one from Malaysia, another from Philippines. They introduced this energy planning. And we have also looked at some isolated energy systems, financial planning, and so on and so forth. So there is some space remaining where in future I'm going to add maybe some of your works as a part of this pinch presentation. So essentially what happens is pinch analysis was originally started with a conceptual process integration approach, but then it has been evolved to develop many simple and efficient algorithm by exploiting spatial structure. So what is that simple and efficient? The original problem that we have discussed today about the heat exchanger network is basically linear programming. If you want to solve it through the simplex technique, the complexity is square of the number of variables. Okay, so if you had n streams, so your number of variables, you can say in a sense represented by n, so your complexity is n square. On the other hand, if you do the pinch, the complexity is square root of n. So this is in that sense 4 times faster. Okay, the pinch. Not every problem, because of the spatial structure of it. It has been applied to various industries, various processes, and various ways. Okay, from renewables to the hardcore processes. It has been started evolving as a dynamic tool. Okay, from heat exchanger network to various other applications. I think I have just quickly shown you some applications. Okay, various industries: food, paper, dairy, whiskey, cement. Okay, and in the very beginning I highlighted you about the applications to the textile industries. And that's all from my side. I'll end with a title of a paper of Budolenov. He says, use pinch analysis to knock down capital costs and emissions. So I think I'm in time, 12:30, exactly 12:30 now. So if you have some questions, I'll be very happy to answer.
Thank you very much, sir, for the wonderful, insightful lecture. Definitely, participants got benefited out of it. They got the glimpses of the pinch analysis applications.
Thank you. Thank you very
Sir,
much.
there are a few questions. As such, we can say you can also see in the question box. See,
the problem is I really cannot see the questions in the. So you have to tell me what are the questions, because it seems the box is too small and I can't. Okay, now I have taken it out. Okay. Okay, one question has been asked by Balaji. He said the pinch temperature is in the optimization, is it compulsory to be in the 9 to 10 degree? Okay, no. Again, it depends on the process to process application. So it can be something low as 4 to 5 degree. That is the temperature difference, not the pinch temperature. Pinch temperature is the temperature at which the delta T occurs, minimum delta T. Okay. Second question is the designing of heat exchange network S-10 energy analyzer is software used. Okay, you can use the S-10 simulators or S-10 Energy Plus to do all this targeting, but it can be done even with simple Excel. So I have shown you how it can be done in tables. You don't even need an Excel. A pen and paper is good enough to solve all this question. Okay.
One question is from Taruna Jain, and she's saying that kindly repeat how the sign is decided in second row, that is
Okay,
MCP sign.
Right. Okay, now I could see that. So yes, ma'am, what happens is we just decide that one side is inlet, another side is exit, okay, or demand. So inlet side is positive, exit side is negative. Okay, that's the convention we use. You can use the other way around also, but you have to be consistent.
And Siddhant is having required some sort of information how the graphs are separate at pinch.
Right, but that is by design. Yeah. We have one hot composite curve, we have a cold composite curve, we place them together, one below the other, and then we'll start shifting them so that their difference, that is the temperature difference, becomes exactly equals to delta T main.
I think that's all.
Okay. Is there any other question that I missed?
No, sir. I think that's all of the questions from the participant.
Okay.
If Dr. Maiti is there, hello, Dr. Maiti is there. Can you give the concluding remark? I think he's, not been at his location. Yeah, he's coming.
Sir, I think it would be better to give the concluding remark by you, sir, because mostly it is related to mechanical, electrical, all these things.
Yeah. Okay. It's okay. Basically, the pinch is started as I said, it's very simple, and only the heat exchange related problem, but it is grown to the full-fledged industrial tool for the various applications, and which is we also discussed over here with the powerful pinch analysis. Power of the pinch analysis, I think you got just in the glimpses. There are full-fledged 5 days short-term training programs also in IITs. At least once in a year it happens related to the pinch analysis, and where most of the major application related to the heat and water are covered, and others are introduced. So those who are interested, they can take the that particular course. This particularly with this, I thanks once again Professor Santanu sir taking out the time from his busy schedule and sharing his experience with all participants. Thank you, sir, for your excellent lecture related to the pinch analysis applications in various domains, including the textile also. Thank you very much, sir.
Thank you all. Okay, and thank you, especially thank you, Professor Mukund Bade. Okay, it's nice interacting with you after so many days, and I just request all of you to stay safe, okay, and be well. Okay, bye. Thank you very much.
Thank you very much. Yeah. Okay, sir. Thank you, sir.
Thank you.
Yes, sir. Thank you, sir. Next session is going to start at 2 o'clock, so be there at 1:50 for the participant. Thank you, and we are ending this meeting. Dr. Vivek, if you are there. Hello, Dr. Vivek. Please join the meeting for 1:50 p.m. All the participants are requested to join the meeting, the second session at 1:50 p.m.